Hi, I'm Spider-Man and welcome to our lesson on calorimetry. This is an introduction to calorimetry. I have a video up which goes through the steps of solving calorimetry calculation problems. So calorimetry is the process of measuring heat changes in a chemical reaction. To do this, we use a device called the calorimeter. There are two common types of calorimeters that we will discuss in this lesson: the coffee cup calorimeter and the bomb calorimeter. The coffee cup calorimeter is a simple and inexpensive device that is commonly used in undergraduate labs. On the other hand, the bomb calorimeters are more complex and expensive, but they allow for more accurate measurements at high temperatures and pressures. There is a coffee cup calorimeter diagram on the left. It is important to understand that in calorimetry problems, including the coffee cup calorimeter, the substance reacting is the system, and the water and the calorimeter make up the surroundings. The system and surroundings exchange heat, and this heat is what is measured. The change in heat of the water is calculated, which allows us to determine the change of heat for the system. Now that we have a basic understanding of calorimetry and the different types of calorimeters available, let's talk about some important equations and formulas that are commonly used in calorimetry. The first equation is the mole equation, which relates the number of moles N to the mass, lowercase m, and molar mass, uppercase M. It is written as N equals mass over molar mass. N equals m over uppercase M. The next formula is the heat of surroundings formula, which relates the heat absorbed or released by the surroundings Q sur to the mass of the substance, lowercase m, the specific heat capacity C, and the change in temperature delta T. It is written as Q sur equals m times C times delta T. We can also convert the heat of the surroundings to the heat of the system by using the equation Q sur equals negative Q reaction, where Q reaction is the heat of the reaction. Lastly, the enthalpy of the system or reaction, delta H reaction, can be calculated by using the formula delta H reaction equals Q reaction over moles, where Q reaction is the heat of the reaction and N is the number of moles. So in this slide, we will discuss a key concept in calorimetry, specific heat capacity. So specific heat capacity is defined as the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. It is usually represented by the symbol C and has a unit of joules over kilograms times degrees Celsius. It is important to note that there are different units of heat measurement, such as joules and calories. 1 calorie is equal to 4.184 joules, and 1 calorie with an uppercase C, which refers to kilocalories, and it's equal to 1,000 calories, or 4,184 joules. These are examples of specific heat capacities of different materials, like water, aluminum, and such. By the way, understanding specific heat capacity is crucial in calorimetry because it allows us to calculate the amount of heat absorbed or released by a substance during temperature change. So, as we've learned that calorimetry allows us to measure the heat changes in a chemical reaction or physical changes, in this slide we will review the relationship between the heat absorbed or released by the system and the heat absorbed or released by the surrounding. So I talked a bit about this in the Introduction to Thermochemistry video. I recommend watching it. So remember, for an endothermic reaction, heat is absorbed by the system from the surroundings. Therefore, the heat of the reaction, Q reaction, is positive. This also means that the heat absorbed by the surroundings, Q sur, is negative. This is because energy is being lost by the surroundings, resulting in a decrease in temperature. On the other hand, for an exothermic reaction, heat is released by the system to the surroundings. Therefore, the heat of the reaction, Q reaction, is negative. This also means that the heat absorbed by the surroundings, Q surroundings, is positive. This is because energy is being gained by the surroundings, resulting in an increase in temperature. So in this slide, we will discuss the relationship between heat, Q, and enthalpy change, delta H, in a chemical reaction. We have learned that heat absorbed or released, Q, in a reaction is specific to the amount of substance in grams. If more of a substance is reacted, then more heat is absorbed or released. On the other hand, enthalpy change is the same thing as Q, except it specifies to the amount of moles, not grams. This means that the enthalpy change delta H is independent of the amount of substance used. In other words, the relationship between Q and delta H is given by the equation delta H is equal to Q over N, where N is the number of moles. It is important to understand that it is important to understand the relationship between Q and delta H, as it allows us to make comparisons between different reactions and to understand the energy changes on a molar basis. So this concludes our lesson on calorimetry. A video of me solving calorimetry problems is posted on this channel. Thank you and bye.